Jai Hind all of you. I am Mohan Sharma, Assistant Professor from Ajay Kumar Garg Engineering College from the Department of Electrical and Electronics Engineering. In this video lecture, we are going to cover a topic which is economic load dispatch, and it is basically useful for final year students of Electrical and Electronics Engineering branch and Electrical Engineering branch in the University AKTU, and the subject code is KEN 070. So let's begin it. So firstly, if we talk about economic load dispatch, so what do you understand by economic load dispatch? Firstly, we will talk about load dispatch. So you know, the load we are talking about is the basic load which is actually the power system load, and that load has to be satisfied by the generator. So in this we must talk about firstly that how the power system works. So there are three segments of power systems. First is generation, second one is transmission, third one is distribution. So the third one, that is distribution of the power is among the load, right? So the load is which we are utilizing whatever appliances we are using, that becomes load, and the industrial load is there, the college load is there, just like residential load is there, right? So many factories are there, so whatever the equipment is there, so that becomes a load over here. Now this load has to be satisfied. The meaning of satisfaction of the load is that whatever the amount of power is required by the for operating that load, that appliance efficiently at the rated condition, is known as satisfying the load. Now this load is satisfied by the by the generator, and that generator is installed in the generation part, right? Now that generation part is basically that power is generated by the help of thermal power plant, nuclear power plant, hydro power plant, or recently our shift is from traditional to conventional to non-conventional energy resources, just like renewable energy resources. So a number of power plants are utilized for generating the power, right? Now how much amount of power is required for generation? It must be equal to the load demand. So whatever the load is demanding, so that much amount of power has to be generated by the system. Now this generation is basically generation basically deals with transmission losses, power demand, reserve capacity. Okay, so it has to be maintained equation or an equilibrium is there. So the generated amount of power must be equal to power demand, power losses, and that reserve capacity of the system. Basically reserve capacity is the amount of power which is required by the power plant, which acts as a reserve for the system, right? Now the main aim in the economy of operation problem is to minimize the total cost of generating power, real power, at various stations. So firstly, it must be understood that the real power is generated in the generator. Now at the various stations, while satisfying the load and the losses in the transmission link. So what I was saying, the power has to be satisfied that particular amount of load and losses into the system, right? So basically the losses, most of the losses will occur into the transmission system only. Okay, and if we talk about the transmission system, we have short transmission lines, medium transmission line, long transmission line, and most of these losses are in long transmission line, right? So these losses has to be satisfied. Now economy of operation is naturally predominant in determining allocation of generation to each station for various system load levels. So what is this? Basically you have to assign the amount of load at various generators. So let us take an example. If we have an area, just like see, we have an area 1 over here. Okay, this is area 1, and this area 1 has 700 megawatts of load. Okay, so this 700 megawatts of load has to be satisfied by the generators. And what is the let us say we have two generators, one is of 400 megawatts and other, let us say other is of also 400 megawatts. So now this 700 megawatt of load has to be satisfied by both of these generators. Now How you can satisfy this load? So yes, the load can be easily satisfied by both the generator. One can operate at 400 megawatts, other can operate at 300 megawatts, right? So this is a very easy case in which the allocation is properly distributed. Now if you have some other generators, just like 3 generators or 4 generators of less power capacity, so under that condition you have to have the combinations in which the load can be distributed among those generators, so that all the generators, all the generators must be working in efficient manner. Okay, so this is actually known as optimal operation, that is operating the system, operating the generators optimally, right? So this has to be done, and allocation of generators for each station for various load levels, right? Now the first problem in power system is called unit commitment problem. This is important one. Okay, so unit commitment problem. So what do you understand by unit commitment? See, the word unit utilized here is treating your generator. So basically the unit is representing generator over here, and the commitment is basically turning on. So we are turning on the generator or a power plant, so that the power plant can satisfy that particular load. So that amount of that amount of generation can be carried out, or can be the amount of power can be generated from that generator, right? So this is the problem, and how this problem will be satisfied? See, there is another problem which is known as second one is known as load scheduling problem. So both these problems are basically very much important to satisfy economic load scheduling, or to just treat, or we can say that to have the schedule in which the system or the generators will operate, right? So economic load scheduling or economic distribution is basically distribution of the load on this system, and the load scheduling is the we can say the timetable of the this one different types of generators, at which time, for how long this generator will operate. Now economic dispatch is the online economy dispatch. So online economic dispatch, what do you understand by this one? Online economic dispatch is, that is, the generator is generating power, it is connected to the grid, and during this scenario only the generator is satisfied, or generator has to take the load. So this is known as online economic dispatch. Okay, wherein it is required to distribute the load among the generating units actually parallel with the system in such a manner as to minimize the total cost of supplying the minute to minute requirements of the system. So minimizing the total cost is your ultimate goal, right? So this is our criteria, or this is our main constraint that has to be satisfied for working of the system, right? Now we talked about constraints. So what are the system constraints? These constraints are basically the factors which are upon which the working of any I must say any machine or any process depends upon. Okay, so there are factors upon which or the factors which affects the performance of a machine. Okay, so these are constraints. So basically there are two type of constraint. First one is equality constraint, and second one is inequality constraint. So firstly we will talk about the equality constraint. What are those equality constraint? So equality constraint is, so the equality constraint are the basic load flow equations. So what is the basic load flow equation? Load flow equation is basically the if in layman language, if we talk about the basic load flow equation, so it is actually the PG, that is generated power, PG must be equals to PD plus PL plus reserve capacity, right? So this is actually the load flow equation, or we can say that the equilibrium equation that has to be satisfied. Now load flow equation, you must have studied about the load flow equation when you have studied about the load flow analysis, right? LFA. So there were several methods by which you can have the load flow analysis, just like Gauss-Seidel method is there, Newton-Raphson method is there, fast decouple method is there. Okay, so by those methods you can have the load flow analysis, but here we know that this is a load flow equation which is for real power and reactive power. Both these powers can be calculated, which is given by summation Q is equals to 1 to N, that is EP multiply by EP GPQ plus FQ BPQ plus FP multiply by FQ GPQ minus EQ BPQ. Okay, and basically if we talk about the P over here, this is the real power, and what is this P? This P is the number of generator which we are talking about, right? So if let us say we are having n number of generators over here, so we can say that this is for first generator, and for Q is equals to 1 to N. For you can have all these, or we can say that the total real power generated over here can be represented by this equation. Similarly, you can have reactive power generation over here. So what is reactive power generation? Q is equals to 1 to N multiply by FP EP GPQ plus FQ BPQ minus FQ GPQ minus EQ BPQ, this one. Okay, so by this you can have real power and reactive power, and this is reactive power. Okay, so by this you can have your equality constants. So we'll talk about inequality constants now. So basically you can say that equality constants are those constants which directly affects the operation, or inequality constants can be said can be treated as indirectly affecting the system. Okay, so the first one, that is the inequality constant. In the inequality constant, the first one is generator constant, the generator which is connected over the generation part. Second one is the voltage constant, the voltage which is generated by that generator. Transformer tap changing, so whatever the transformer is there, so if it is this auto transformer or a 2-winding transformer, depending upon the type of the transformer, what is the tapping which are used on those transformers. Then transmission line constraints, so you have transmission line links over there, so when the power has to be transmitted over with the help of transmission lines, so there are several losses, there are several constraints upon which the transmission transmission losses depends upon. Last one is network security constraint. So security is another very much, or we can say that a very large topic, so that security of the system has to be taken care of. So there are several constraints, so we will talk about them one by one. First one is generator constant. So the kVA loading on a generator is given by this one. Okay, so what is this? It is under root of PP square plus QP square, and basically if we talk about this will give you, this one is this will give you the root mean square of all these quantities. Okay, so it is given by this one, and this should not exceed a pre-specified limit value which is Cp, and because of this because of the temperature rise condition, that is PP square plus QP square must be less than or equals to Cp square. Okay, so this is the predefined condition, pre-specified condition, so that the range of the, or we can say the threshold value of this particular value is less than or greater or less than or equal to Cp square only. Okay, so this is how the generator constant depends affects the process of this generator. Second one is voltage constant. So it is essential that the voltage magnitude and the phase angle at the various nodes should vary within the certain limits of the, okay, so certain limits, so there is a limit, and under that limit only the voltage and the phase angle of the system must lie. Okay, so yes, the voltage magnitude and the phase angles of this must lie within the certain limits. The voltage magnitude should vary within the certain limits, because otherwise the most of the equipment connected to the system will not operate satisfactorily, or additional use of this one, additional use of voltage regulating device must be connected, and it will be obviously uneconomical. So here if we talk about the power quality of the system, okay, so what do you understand by power quality? The power quality is basically the reliability of power. Okay, so the main constant is reliability. So what do you understand by reliability? If I am taking power from a utility, so my main aim is that I must get the constant amount of voltage for regular interval of time. Basically we can say that it for uninterrupted supply must be there. So this is power quality. Okay, so for maintaining the power quality, your this voltage, that is the generated voltage or the voltage which is available at the load, must be equal in this limit Vp minimum and Vp maximum. So this is the range in which the voltage must lie, and you will have delta over here. So this is the load angle that must also lie between delta P minimum and delta P maximum. Okay, so these are the basically limits of the operation for voltage and phase. Third one is transformer tap setting. So what is transformer? So we all know that what is transformer, and there are several types of transformer used in the power system, and one is auto transformer and another is two winding transformer. So if an auto transformer is used, so auto transformer is basically one winding transformer in which the same winding is utilized as primary as well as secondary. So if you have one winding auto transformer is there, so in this auto transformer what you can do, you can have the minimum tap setting could be 0 and the maximum tap setting could be 1 over here, right? So this T is basically the tap setting, and it is lying between the 0 and 1. So why 0 and 1? It is basically in the if we talk about single winding, so it is basically into the percentage. So if you are using complete winding, okay, so the tap setting is 1, and if you are using 0 windings, then it is 0. Okay, so although if it is 0, that it will be 1:1 transformer. Now similarly for two winding transformer, the tappings are provided on the secondary sides, right? Obviously primary side is given supply, and from the secondary side supply is taken care of, and it is connected to the load side. Now here secondary side, what happens over the secondary side, there are tappings, and which tapping is utilized is treated as that tapping, and it comes under 0 to N. Okay, so what is N over here? N is the transformation ratio, and this is the transformation ratio, that is ratio of transformation, V2 upon V1, I1 upon I2, K2 upon K1, basically N2 upon N1. This is the number of turns. Now lastly, the phase shift limit of the phase shifting transformer. So here also phase must be taken care of similarly, just like delta. So here theta is in the range of theta P minimum and theta P maximum, right? Now transmission line constraints. So what are the transmission line constraints? Transmission is there. Transmission is basically the amount of power which is transmitted from this one generation to the distribution, right? So what is the transmission line constant? The flow of the active and the reactive power through the transmission line circuit is limited by the thermal capability of the circuit, and which is expressed as Cp must be less than or equal to Cp maximum. So Cp is basically what we have talked about. Cp was the one factor which was told over this one. This is the Cp. Okay, so this is again utilized in the transmission line constraint. So that must be expressed as Cp must be less than or equals to Cp maximum, where Cp maximum is the maximum loading capacity of the pth length. So what is pth length? So you have transmission lines of several lengths. So this is the pth length transmission line, and it must have maximum Cp as Cp max, right? Now lastly is network security constraints. So whatever the security constraints are there, that comes into the existence. Now if initially a system is operating satisfactorily and there is an outage which may be scheduled or forced. So here you can see this is scheduled or forced outage. So what do you mean by outage? Outage is basically the interruption in the supply. Okay, so if you have power failure, that is treated as outage, and there are two types of outages. First is scheduled outage, second one is forced outage. So scheduled outage is basically pre-scheduled is there. So if we talk about the machine has to be undergo some maintenance process, so you have to remove that machine from the supply system, and we say that machine has to be taken offline, and when offline the machine is taken offline, under that condition you can say that the machine is scheduled outage, machine is under scheduled outage. And second one is forced outage. So what is forced outage? Forced is something which is unintentionally, right? So it could occur anytime. So just like fault, so if due to any faulty condition the machine has to be go offline, so under that condition we will say that the machine is under forced outage condition. right? So forced outage, it is natural that some of the constraints of the system will be violated. Obviously, if scheduled outage or forced outage, where any kind of outage is there, so we will say that this is some constraints are being violated, or the values of the system is going out of the limits, right? Now the complexity of these constraints is increased when a large system is under study. So whenever you have a large system, basically if you talk about the power system is a very large system, and in that power system, what do you do? The power system, there are number of transmission lines, there are number of buses. So calculate or analysis of all these machines, all these buses becomes very complex. And if we talk about the whole power system, which is a basically very complex network, right? So its study becomes although further more complex. Now several characteristics through which we can have the idea of how the thermal power plants will operate. Okay, so in that, the first characteristic is input output characteristics. So if we talk about simply thermal power plant, let us say thermal power plant. So in thermal power plant, what will be the input, what will be the output? So for answering this, you must know how the thermal power plant operates, what is the basic function criteria of operating a thermal power plant. So thermal power plant, in this we know that there is coal which is taken as a fuel of the thermal power plant, and that coal is burnt into the furnace and it produces heat. That heat is utilized by the boilers to boil the water, and that boiler is converted to the steam, and steam temperature is further raised in the superheated converted into the superheated steam, and that superheated steam is injected over the turbine, which rotates the turbine is connected to the rotor of the generator by a shaft. Combiningly both rotates at the same speed, and rotor rotates, it cuts the flux. Faraday law of electromagnetic induction generator generates the electricity. So this is how the power is generated from a thermal power plant, right? So for operating all these processes to take place, the thermal power plant takes 10 to 12 hours to operate, right? So although we'll talk about these things when we talk about the scheduling problems. So basically thermal power plants are utilized for base load satisfaction. So satisfying the base load, you must operate thermal power plants. So here we know that if we talk about the input of the thermal power plants, input is coal, that is heat, and output is power, that is in megawatts. So input output curve can be drawn over here, and here what we will take, the input output curve of a unit can be expressed in million kilocalories per hour. Okay, million kilocalories per hour, right? So million kilocalories per hour, that is basically the amount of heat which is produced in 1 hour. Okay, so that is the input. So here we have taken million kilocalories, or it can be taken as directly into the rupees per hour, that is for 1 hour how much rupee coal is required or consumed, that is known as rupees per hour. Okay, so this is fuel or this is megawatts. So input output characteristics. Okay, it comes out to be approximately straight line, although it is little bit curvy. So this is known as, this is basically curved nature, or it is of curved nature. This is P minimum and this is P maximum. So the generator will always operate within this range. So generator will never operate over this range, and you must not operate the generator in this also. Okay, so this is the first characteristic, input output characteristic. Second one is incremental fuel cost. So what is incremental fuel cost? See, you have this one. Okay, this is fuel and this is P. So if you have this segment, so in this you can see that this one is delta F and this one is delta P. So delta F upon delta P, what you will get? Delta F upon delta P is basically slope of this line, right? So this is basically actually this is the change in the load, simply a small increment into the load demand, and depending upon that load demand, or to satisfy that particular load demand, this delta F amount of fuel is required. Okay, so this is basically known as incremental fuel. So that is basically this curve. Okay, so incremental fuel cost is basically, it is the ratio equal to the small change into the input to the corresponding small change into the output, right? So similarly, this is incremental cost, that is IC, and this is power output in megawatts, although the curve is almost similar in nature, right? Now methods of solving ELD, so that is economic load dispatch. So firstly we can have by neglecting the transmission losses. Secondly, we will have we will talk about with considering transmission losses. So firstly, by neglecting transmission losses, we are having several constraints or several parameters. First is FT. What is FT? It is the total fuel cost, total fuel input to the system. Fn is the fuel input to the nth unit. PD is the total load demand, and Pn is the generation of the nth unit, right? So all these parameters are known over here. Now to satisfy the economic load dispatch problem, you know, this equation must be satisfied, or economically, if we talk about economically, the cost should be minimized. So minimum of FT, that is this one, total cost, must be equal to summation n is equals to 1 to n Fn. So fuel input to the nth generator, that total fuel must be less than, where that is minimum, subject to PD, that is the load demand, whatever the amount of load demand is there. So PD must be equals to summation n is equals to 1 to n Pn, right? And there is a factor which is known as Lagrangian multiplier. So here we can use Lagrangian multiplier, that is, which is delta over here, and here you know that df1 upon dp1, which was the incremental cost. Okay, so incremental cost of first generator, IC cost of second generator, IC cost of third generator, all these generators must be equal to a constant. That constant is known as the Lagrangian multiplier, lambda, right? Here this one, df1 by dp1, is the incremental cost of the generator at plant 1, and its unit currency, and its unit is currency in the per hour. Okay, so this is how we can have this method of solving ELD by neglecting losses. So although in practical scenario losses cannot be neglected, there are a lot of losses are there. So we have to consider losses over here. So 1, 2, 3, 4, all these parameters are same, which was considered earlier. Now we have PL, that is the total loss of the system. So it is the total loss, right? Not of the first generator or not of the second generator, it is the total loss, right? So if losses are considered, the optimal load dispatch problem including transmission losses is defined as this one, that is minimum of FT is equals to summation n is equals to 1 to Fn, and subject to PD plus PL is equals to summation n is equals to 1 to n Pn, right? Now when you solve this with the help of a Lagrangian multiplier, solving this equation using Lagrangian multiplier, again what we get, we arrive on this situation, that is Pn is equals to 1 minus Fn upon lambda minus summation m is not equals to m in this case, 2 times of Bmn Pm upon Fnn upon lambda plus Bmn. So this is the Pn over here, which is the generation of the nth generator, and if with a certain coordination equation we written as Fnn Pn plus Fn plus delta summation P 2 times of B to B 2 times of Mn Pn is equals to lambda. So by this coordination equation you can have the amount of this one P generated over here, right? So this was by considering the transmission losses. So there are several coefficients. So firstly we'll talk about the assumptions which are taken while having the coefficients. So the first one is, there are two assumptions. The first one is the ratio of the transmission line is same, the ratio must be same of, and the phase angle of all the load current in it must be same. So by doing so you will have this equation where all these coefficients B11, B12, B21, this is basically for two transmission lines. So these are the basically the transmission constants which will if you solve the numericals, or when you will have to schedule the load, so under that B11, B12, just like these constant comes under picture. Now you can have loss coefficients over here. So this is for 3 different cases. Okay, so this is loss coefficient, and yes, that's all for today's lecture. Thank you very much. Jai Hind.